Hello, everyone. I'm Vishaka, and I welcome you all to the LIGO India series Behind the Scene. Today, we have with us Dhruva Ganapathy. Currently, he's a six-year Ph.D. student at the MIT. And before starting his grad school, he completed his engineering physics at the IIT Delhi. And currently working on the quantum enhancement of the LIGO detectors using a technique called frequency-dependent squeezing. I welcome you, Dhruv. How are you today?
Good. Thanks for having me here.
Thank you
And
so much for giving us your time.
Mhm.
What drove you to pursue astrophysics as a research career?
So I first got interested in astrophysics, especially before I started college. I did this online course in X-ray astronomy, and somehow I found that like really interesting. When I was just 17, and I didn't really know much about anything in physics, but I thought that that's really cool that we could um, gather a lot of information with very limited resources, and like especially that's how astronomy and astrophysics works. You just all you have is the light from space, and then you're able to tell a lot about what's out there. So I found that extremely interesting. But when I started undergrad, I actually changed direction quite a lot. I was really into quantum mechanics as like when I was starting out my undergrad. I really enjoyed studying quantum mechanics in both my chemistry and physics classes. And I started going into quantum information, and I spent a lot of time doing quantum information. It just so happened that I eventually found a project that kind of mixes both. Like I got into quantum squeezing for LIGO, which although driven by the similar astrophysics goals that I was excited by when I was 17, on a day-to-day basis, it involved what I was actually interested in at the time, which is quantum optics and quantum information. And yeah, I think over time, I think that's what I've grown to become interested in. I'm definitely see myself as an experimentalist who
That's
had
great.
really like anything that's quantum.
So how did you find quantum interesting? Could you please briefly tell me about this?
And all of us who have done school in India and have taken science in 11th and 12th, there's this one part in chemistry where they teach you about what the orbitals are, what the SPD and F orbitals are.
Absolutely.
And there's, to be honest, they like it's something I kind of just took at face value when I was in 11th. I was just like, okay, the S orbital is shaped like this, the P orbital is shaped like this. I didn't know what it meant until in my first year of college, in my chemistry class in the physical chemistry section. I was shown for the first time that if you solve the hydrogen atom, like the hydrogen atom Schrodinger equation, to get the quantum mechanics, then these then the solutions looked like what we had been taught the orbitals were. So I thought that was really cool. Things started to make sense. And then I was introduced to the idea of quantum computing, which also I thought was really cool. I think simple things like how you can do things like quantum teleportation, stuff like that. I think that's what really got me into the field.
So I'll just move to the next question.
Mhm.
Briefly, could you please tell me all the hardships that you went through while you were in your field? I mean,
Um,
field is not very easy, right? You tend to get up, a little messed up, probably tired, and going through the same thing again and again. And as you told me that, for the past 5 years, you have been doing the same thing. So how is the experience?
Um, so it's been interesting. I would say that a lot of the hardships you face in research are not very different from what hardships in any other field would be. I think, or at least for me, a lot of them are not as much don't have as much to do with the academics and research of what I do, but more with just regular life and growing up. As you start grad school when you're barely out of college, and I was 22 when I started grad school. So it's like that. Um, so that's that period of like going from essentially going from being a kid to being an adult. I think that that's in its own way it's hard for everyone. But um, what what was especially hard about grad school for me, at least in my first year, again, I've been very lucky. I've had a very supportive environment over here. I've had a lot of mentor figures, a lot of people who are extremely patient and have been willing to teach me literally everything that I know right now. Um, but it is a different experience when you start working on a research project. You're thrown into something where you're expected to take a lot more responsibility and control something than you would have done previously as an undergrad. You're expected to move along with less supervision. I think you have to get idea with the okay with the idea of not knowing what's going on. I think that's something I took a lot of time getting used to because I I mean for whatever work I'd done in my undergrad, it wasn't anything compared to what I would do as a grad student. So there's a lot of figuring out how things work, um, especially
So
with
the
experiment.
transition was huge, right? I mean, like, t-
Yeah.
so how did you exactly cope up with it? I mean, like, was it easy for you? I mean,
Think it was easy or hard. I think everyone who does, at least I can only speak for experimental physics here, but I think everyone goes through the same process. You come in with some idea of physics, and then you realize that the things that are actually important for experiment are very different from what you've been taught as an undergrad in your classes. You start having to care about a lot of things that you weren't taught as an undergraduate, like electronics, controls, all of these things. And I think it was, for me, I don't think it was very different from what other people go through. I think it took me a similar amount of time to get used to things. I think what made things hard for me, in my case, would have been COVID, because that I think took out a solid two chunks of my 2 years, a solid chunk of 2 years of my grad school. It was just we were still going to lab, like me and the other grad student who's working on my project, but being cut off from just regular human interaction was in a way quite demotivating. And I think over time it's made me realize something about myself, that for me it's not just the science that drives me, it's actually the people doing it and
around you.
getting to interact with people. So at least for me, science has turned into something that's very, I think, a very human oriented endeavor. So I think um,
Okay.
the lack of human contact was pretty taxing.
So, okay, moving on to the next question. You have been working on the quantum enhancement of LIGO detectors for the
Mhm.
past so many years. So, could you tell me more about it and how will it impact the research in the coming years?
Okay, so I mean, I can start with the basic idea of noise in the detector. Now, I'm sure a lot of people who are familiar with LIGO know the basic principle of how LIGO works. It's an interferometer. It's got two arms. You split a laser, you recombine it, and you use the interference pattern to back out what length displacements you're seeing in both arms. Um, but obviously, whenever there's a signal, there's also noise. There's many different kinds of noise in the detector. I mean, I think that the reason LIGO is such an insanely complicated experiment is because they've spent decades trying to figure out how to lower all of these different kinds of noises. one of the very, very fundamental sources of noise is from the quantum mechanics of the laser that's used in LIGO. And that basically comes from the idea that if you were to actually look at what light truly is, it's not a simple wave as is described for in a lot of, like, in the basic picture of interferometry, you have a wave that completely cancels with itself to produce destructive interference. It's actually, this is where the particulate nature of light comes in, I think. So the true picture of light is something between a wave and a particle. And effectively what this results in is that you can still think of it as a wave, but it has some fuzz over it. It has some uncertainty, and this uncertainty is fundamental. It comes from quantum mechanics, um, and what we're trying to measure when we're doing interferometry is we're trying to measure the phase difference between two different waves. When you're recombining based on their at the beam splitter, based on their phase difference, they're either going to constructively interfere or destructively interfere. But if there's uncertainty in the phase of any of these waves, then there's uncertainty in your measurement. So for a laser light, which is I would say vanilla quantum state you can come up with, which is the most I think easy to understand in terms of a quantum state. It's just it has some uncertainty in phase and it has some uncertainty in amplitude.
Amplitude. Yes.
And in whatever units they're equal. So it looks like this uniform fuzz that's all over the wave. Now, what quantum mechanics tells us is that the uncertainty in phase and the uncertainty in amplitude, pretty much just like you mentioned, the uncertainty in velocity and position, they are conjugate. So you can't actually reduce one while keeping the other constant or reducing the other. You have to reduce one at the expense of the other one. But luckily in LIGO, we only care about phase measurements. There's a caveat to this, which I'll come to. But when you reduce the uncertainty in phase, you get better measurements. Now, how can you reduce the uncertainty in phase? There are two ways of doing it. One is just increasing the laser power in the interferometer. That comes with its own host of problems. It's actually it sounds like a very easy thing to do. You just turn up a dial, but it's a very complex procedure in the interferometer. It messes up with a lot of things. It changes the geometry of the mirrors by heating them a little extra. It creates all these different instabilities everywhere. So what people have been thinking of, and an idea that was first proposed in the 80s by Carlton Caves, is that we can use this quantum state of light called squeezed light. And what this does is this does this trade-off. It reduces the uncertainty in phase for the uncertainty in for extra uncertainty in amplitude, because you don't really care about the amplitude as much. Um, you can inject squeeze light into your interferometer and you can get better measurements. Now, and squeeze light was first. It has been demonstrated for a while, but it was first used in working interferometer network during the third observing run of LIGO in 2019-03, where both the LIGO detectors and the Virgo detector used squeezed light and saw a huge enhancement in their sensitivity. Now, the caveat to this is that while I said that we don't really care about the amplitude, this is true at most frequencies, but at low frequencies, what happens is that any uncertainty in amplitude results in uncertainty in the radiation pressure on the mirrors. So there's a lot of power of light. There's a lot of power that the laser has in the arm cavities of LIGO. And you can think about every photon as, imparting some momentum to the mirror. So it's causing the mirror to rumble a little bit. And if there's uncertainty in this amplitude over here, then there's uncertainty in the force on the mirror, and that's uncertainty in the position of the mirror position, and that happens at low frequencies. So we call that radiation pressure noise, and this whole phenomenon is called optomechanics because there's light, there's mechanics involved. So the more you squeeze to get better phase measurements, the worse you make this radiation pressure noise at low frequencies.
Correct.
So my specific project was using this technique called frequency dependent squeezing, where at low frequencies, instead of squeezing phase, now we're squeezing amplitude.
Okay.
And as a function of frequency, we change what's being squeezed. So now we see broadband enhancement. So that's what I meant by broadband. It's like at low frequencies, we reduce amplitude noise, so we reduce radiation pressure noise. And at high frequencies, we reduce phase noise. Doing this in practice involves, at least at both LIGO sites, it involves a 300-meter optical cavity called a filter cavity. Our paper is getting published pretty soon, so this will be.
Yes,
Uh,
and how, yes, of course, you told me about that, that it's going to be, your paper is going to be published very soon, right? And the Caltech is doing a feature in it. So,
yeah.
anything, you want to tell us more about it? How excited are you about it?
Um, I mean, I'm really happy it worked. I I spent a year at LIGO Hanford commissioning the frequency dependent squeezing system, and it was it was exciting. I think people on site are wonderful, but it was also a huge time commitment. It meant me being away from here, away from MIT, from all my friends, which was hard. But it was just glad to see that at the end of the day everything worked.
Yes.
So the true astrophysical impact is that now we've been able to extend the astrophysical range of LIGO even more. Both detectors are currently observing at close to 160 megaparsecs out, compared to O3, where Hanford was at 117 and Livingston was at 130. So
So now you also know that LIGO India has been approved by the government of India. So for you, how big this is and how will the gravitational wave research uh, impacted by this?
um, I'm not an expert on the gravitational wave side of things, but from what I understand, at least, having an extra detector on the map is going to make a huge difference. Especially one that's operating at the sensitivity of the other detectors means that we'll have extremely good sky localization. Right now, because in at least in O4 we've been running with Virgo is yet to come online, so we've been running with two detectors with Hanford and Livingston. So no matter how good their sensitivity has been right now, the localization is kind of bad because with two detectors you can't really localize the signal in space as well. Um, then there are other issues that if one of the detectors is down at any point and a really interesting event comes in, you only see it with one detector right now. It'd be great if you could see it with two detectors. So that's at least that's the benefit of having another detector in the network. uh, I think it's great for India to be running a mega science project like LIGO. It's going to I think it's the most important thing, at least there in that aspect, in my opinion, is that it'll train a whole new generation of scientists.
Absolutely.
And there's a lot of, I mean, there's a lot of knowledge in this whole project, which will, which and where there's knowledge, when you put money into that knowledge, I think it spreads it out more. So and that's something that's exciting for me personally.
The very last thing that I want to ask you here is that you have spent a year at LIGO Hanford commissioning the squeezer subsystem. So how was that feeling, and what was the experience like? You did explain a little bit about it earlier, but how was the experience like?
I mean, it was great, like working on a full scale interferometer. I've had another grad student tell me it's like playing on $1 billion video game. That's what it essentially is like that. There's a lot of, I think it, especially at LIGO Hanford, there's a lot of um, the uh, the environment is very good in the sense that everyone's very patient, everyone's willing to train you. It's a good, I think it's a good place to nurture early career scientists because everyone is ready to help. So that was definitely a great experience. And there's eventually, when you've spent enough time at the detector, there's also people actually do trust you a lot. So I definitely had times where it's just been me and the interferometer. Um,
Okay.
it's great. I think, especially with the squeezer. I mean, like I had already done squeezing at MIT before, but I think working on a big project like LIGO actually taught me a bunch of other things. How do you get things done on a deadline? How do you prioritize tasks? How do you come up with an agenda? Of course, it wasn't me alone. I mean, I've been working very closely with the postdoc who's now running all of squeezing at LIGO. There's very dedicated staff scientists at LIGO Hanford too. Um, but it was still a reasonably small team, like 4 or 5 people max, and it was, I think, the amount of freedom I got um, to at least decide certain aspects of the project I was very happy with. That was also the flip side of like being in the middle of nowhere in Eastern Washington, which was not my favorite thing, but it's a whole different story. But I think overall, I'm pretty thankful for the experience. I think.
Okay, okay, Dhruv, thank you so much. I mean, I'm so glad that I interviewed you today, and I learned so many things from your experience. So, thank you so much for your time today on the behind the scenes blog for us.